Still looking at this 2011 paper from CCEA, Fields and Their Applications, and in this case we're looking at question 5, which is a transformers question. So where appropriate in this question you should answer in continuous prose. You will be assessed on the quality of your written communication. Transformers are electrical devices that are used to change the value of an alternating voltage, and figure 5.1 illustrates the part of the structure of a transformer. In the actual transformer, coils would be wound tightly around the laminated iron core, and there would be leads to the primary coil and leads from the secondary coil. The coils are made from insulated copper wire. And you can see here we've got both sets of coils wound on a central pillar of the core. They've identified the primary coils and the secondary coils, and they've established that this is a laminated core, which basically means that the metal is in layers rather than one big solid block. So what are they asking us to do then? The transformers of this design type have an efficiency of about 97%. Explain how the transformer described above minimizes energy losses. So we can sort of look at the picture and see what there is. Well, we've got a laminated core, we've got primary and secondary wound on the same central piece, we've got this loop of iron around the outside to allow the magnetic field belonging to one to be forced to flow through the other. So there's lots of things going on here. So the mark scheme for this was looking for particular things. It mentions eddy currents. Now, if you're creating a changing magnetic field in this zone, then you're going to force electrons to start forming little currents as a reaction to those magnetic fields. And the little swirling currents that we get in the iron core are called eddy currents. And so how they reduce eddy currents is that they laminate the core. Because the core is then formed in layers, and those layers will then oxidize between the layers, the gap between the layers will oxidize, you cannot get as much current flowing around the iron because it can't cross the layer boundaries because of the oxidization. So a layered core reduces eddy currents, and that therefore reduces any energy loss through swirling currents in the iron. Second source of loss is that when the primary windings field comes out through the coil, in some designs the secondary windings are on a separate part of the loop. In this case the windings are all on the central part of the core, and the core is continuous around the outside. This kind of looped core allows all of the magnetic field belonging to one of these coils to be locked into flowing through the other coil. So this use of a continuous core and all the windings on the central pillar improves the amount of field belonging to one coil that is forced to pass through the other. Another loss that occurs is the magnetic reversal of the domains in the core. You imagine that when the primary coils here produce a field in one direction, then all of the domains have to line up facing a certain way. When that current reverses, the domains have to reverse and face the other way. And there's a little amount of energy loss here in the reversal from pointing this way to pointing that way. And it's generally referred to as like a magnetic hysteresis, the idea that turning a field from pointing one way to pointing the other way requires a small amount of energy. So if you imagine that field starts out pointing this way in the coil, and then the primary coil reverses its current because it's got an AC feed, that then reverses all of these little domains, and that requires a little amount of energy loss and produces heat in the coil. And so that can be basically reduced by manufacturing from a pure form of iron, a soft form of iron that doesn't require very much energy to reverse its domain fields. So the idea of having a good quality iron core will reduce the losses relating to that. The other losses that you're going to get are basic losses in the coils themselves to do with just I squared R, losses to do with ohmic heating in the coils. So basically heat generated in the wires would be reduced by, again, choosing good quality low resistance wires. And that would also be like where you were expecting a high current, they would generally choose thicker wire on that section. So for example, in this case there are a very low number of primary windings and a high number of secondary windings. That would mean that the voltage is going up, so the current would actually be going down. So the primary windings here would be expecting at the same power a higher current because it would be a lower voltage. So they would be selected to have thicker wire to accommodate the higher current expected on those coils. So lower resistance, thicker wire on windings where more current is expected will reduce energy loss through I squared R losses, ohms losses. Okay. So you're sort of turning that into a few little descriptions in prose form. Okay, so the eddy currents, the flow of random electricity within the core, that's reduced by laminating the core because the currents can't flow across the gaps. Loss of field in the transfer from primary to secondary. The use of a looped continuous core with both windings on the central part, that reduces that. Magnetic hysteresis, where the reversal of the domains in the core requires a certain amount of loss of energy, producing heat. That's done by using good quality iron in your core. And I squared R losses in the wires, that's done by having like low resistance wire where you expect high current. In other words, like thicker wire where you expect high current. Okay. So second part then, the primary coil of this transformer with 500 turns is connected to a 230 volt AC supply. Show that the EMF induced in the 2800 turns of the secondary coil is 1.29 kV. So this is just a turns ratio question. So the ratio of the voltage is the voltage at the secondary over the voltage at the primary is equal to the number of turns at the secondary over the number of turns at the primary. So we're looking for the secondary EMF, so we just rearrange for that. And then just input some numbers. So we had a number at the secondary was 2800, voltage at the primary was 230, and number at the primary was 500, and if we shove those in we get 1288, which will be 1.29 kilovolts to 3 significant figures. Part 2 then, the 2800 turns of the secondary coil are wound on the laminated iron core, which has a cross-sectional area of 2.2 times 10 to the minus 4 meters squared. Calculate the change in magnetic flux density every second to cause 1.29 kilovolts to be induced on the secondary coil of this transformer. So we have an equation for the EMF, and it's that it's the delta of n phi over the change in time. And so we are interested here in the B value. So this is basically, it's going to be n delta B A over delta T. And when they ask us then for the change in magnetic flux density, the change in magnetic flux density every second, this thing here is going to be delta B over delta T. So we just rearrange it for that. And so we keep delta B over delta T, and we move the N and the A over to the same side as the E, so we get E over NA equals delta B over delta T. So E was 1290 or 1288 or whatever it was. We'll use their value. And we're dividing then by N and A. And so we fill those in as 2800 for N and 2.2 times 10 to the minus 4, which was given in the question here. And just watch your bid mass here on the calculator. If you don't bracket that on your calculator, you'll end up multiplying by the 2.2 times 10 to the minus 4 instead of dividing by it, which is what's really happening here. So just watch that. And if you do that, you get delta B over delta T equal to 2094. And that should be in like Teslas per second. And that's that.